Hello everyone. Today we are excited to present you about the horizontal well testing. Before we start, let me introduce my group mates. First is me, Yew Kwang Yong. I'll be presenting the overview of horizontal well and also horizontal well testing. Comparison between horizontal and vertical well testing, and also last but not least, the flow patterns encountered in horizontal well testing. Secondly, we have our presenter, Chang Jia Liang, who will be presenting the flow regime and graph analysis. Then, followed by Teang Zhi Chew, he will be presenting the calculations and equations that is related to horizontal well testing. After that, we have Yap Kian Yeap. He will be presenting the advantages of using horizontal well testing. While last but not least, we have Swee Tat to present us the limitations and the improvements that can be made. But first, before we start our presentation, we have to know what is horizontal well. So, a horizontal well is actually a high angle well with a inclination that is generally higher than 85 degrees, drilled to enhance reservoir performance by placing a long wellbore section parallel to the reservoir bedding. Compared to normal well, it is more advantageous because it improves drainage reservoir area, enhances penetration into complex reservoir compartments, and also reduce the gas and water clogging. So talking about the well testing at horizontal well is actually a test where the pressure transient test conducted to determine the reservoir parameters by temporarily imposing alteration in production rate. It is a more complex test compared to conventional vertical well testing. This is due to its 3D nature. Also, this test is very important because it provides valuable reservoir parameters such as skin factor, permeability, length of perforated wellbore interval, and also initial reservoir pressure. Actually, there are three main differences in between horizontal well testing and also vertical well testing. First of all, horizontal well testing has three-dimensional permeability as opposed of one-dimensional permeability by vertical well testing. This is because in horizontal well we have permeability that comes from three directions, which is x, y, z. Secondly, pseudo skin factor is used for horizontal well and normal skin factor is used for vertical well. The reason why pseudo skin factor is used in horizontal well is because due to the partial penetration in y direction. Last but not least, horizontal well has three flow regimes, namely radial, linear, and also pseudo-radial flow. While for vertical well, we have only single flow regime, which is radial flow. So lastly, I would like to talk about the flow patterns in horizontal well testing. As you can see in the diagram, flow patterns are divided into two main categories. They are radial and also linear. Radial can be subdivided into early radial and also late radial. While for linear, also we have two subdivisions, which is early linear and also late linear. That's all for my part. Next, I would like to pass my floor to Chang Jia Liang to present about the flow regime and also graph analysis. Thank you.
Hi, my name is Chang Jia Liang. I'll be explaining the flow regimes of horizontal well testings today and basically the graph analysis of horizontal well testings. Without further ado, let's just begin. So basically you can see the radial flow and the linear flow actually are the two main flow regimes in horizontal well testings, but they're actually categorized into a time-based behavior. Over here we have early time, intermediate time, and late times. So let us begin with this explanations about little bits of this flow regimes in each time zones. So in radial times, radial flow, early later early radial flow, the fluid flow is actually occurring in the y-zig directions, and this is the only regions you can get through skins. And next, before that, this radial flow is actually not affected by both upper and lower reservoir boundaries, but they are actually having a significant difference in this horizontal and vertical permeability. So if the vertical permeability is higher than the others, elliptical flow will occur instead of circular one. And in this linear flow which occur in this intermediate time regions, the fluid flow is in wide planes, whereby it's over here horizontally, and the length of the well is more significant than the reservoir thickness. This occurs actually as a result of the pressure transients reaches the reservoir boundary, either upper and lower. And the linear flow will not occur in a well with pressure maintained by gas cap and aquifer, nor it will happen in a reservoir thickness higher than the length of the well. And for information, linear flow occurs as a result of pressure buildup. And last but not least, we have the pseudo-radial flow. It occurs in the x and y planes, whereby basically it's horizontal well, horizontal behavior, and apparent skin can be determined from these flow regimes, which gives us this wellbore damage and additional pressure drops. For informations, late times flow regimes actually broken down into two parts. The pseudo-radial flow we have just mentioned just now is actually occurs before the other, which are late linear flow. And pseudo-radial flow begins actually when the well flows from the wellbore into the wellbore from beyond ends of the well and the boundaries. And the late linear flow includes the flow from the drainage volume perpendicular to the well, which means the entire reservoir is influencing this wellbore. Pretty much amazing, right? Let's look at this pressure behavior graph. We actually present the pressure difference and pressure behavior in the log-log scale, so we can see this normalized pressure and the pressure derivative plotted on the same graph. So over here we have this vertical radial flow regimes, whereby is occurring in this early radial flow, this in the y and z directions, and after that we have linear flow regimes, and last but not least we have a horizontal, well, in this horizontal flow regimes, whereby it happens horizontally but is still in a radial flow behavior. Pretty much about this pressure graph in a clearer manner, we can see the early radial flow is actually having pressure stabilizations. This pressure stabilizations is pretty much lower than the others because it's actually masked by this wellbore storage effect that occurs directly before this early radial flow, and true skin can be determined from this region, of course. Radial linear flow, you can see the linear intermediate radial flow in this region after the earlier radial flow, and the pressure build-ups is showing us the as a linear gradients upwards. And last but not least, we have this pseudo-radial flow directly after this linear flow, And this is again another stabilization of pressures, but this time around is higher than the previous earlier radial flow because it's not masked by a Weber surge effect. And after this we have linear flow after the radial flow. So you can see the patterns is radial flow, linear flow, radial flow, linear flow. So these are the behaviors of the graph. And importance aspect is we have to find the permeabilities, which are important to our calculations. We can get the permeability of Ky, Kz in this early time radial flow, Ky in this intermediate time radial flow, linear flow, and the Kx, Ky in this late time pseudo radial flow. Let me show you this graph. We're pretty much something about our interest. First of all, we can get the durations of Weber storage effect, where it ends, where it started, and this magnitude of Weber storage effect, the damage, and the estimation of a vertical permeability in the early radial flow, effective length of the horizontal well in the linear flow, and last but not least, this horizontal permeability and reservoir pressure in the late time flow. Thank you very much.
Thank you, Chang. Now, I would like to present the equations and calculations for the early radial flow, early linear flow, and pseudo radial flow. As explained by my colleague, this part of curve is known as the early radial flow. The first equation is a drawdown equation for the early radial flow. And the terms 162.6 Q mu B over the square root of Kx times Kz times Lw is the equation of the gradient. Kx is the permeability in the direction of x. Kz is the permeability in the direction of z. Lw is the length of the completed horizontal well. And the equation of the skin is expressed at the bottom of the slide. The MERF stands for the gradient of the early radial flow, which can be obtained from the plotted graph together with the delta P at 1 hour. This diagram is a layer of formation which is described in a direction of x, y, and z. The horizontal well is at the center of the formation, and Lw is labeled, which is the length of the producing well. The end of the early radial flow region may occur either when the transient reaches the nearest boundary dz from the well, or when flow from beyond the end of the wellbore. Comparing the values obtained from these two equations, the smallest value will be the actual end of the early radial flow. Let's see an example. A drawdown test has been conducted at well A, and these are the data obtained. First, we plot a graph of Pi minus PWF versus time on a semi-log graph. Then, we determine the value of the slope, and we get 8 psi per cycle. Next, we calculate the values for Kx and Kz, and we get Kx and Kz equal to 412 MD. Since the value of Kx is given as 200 MD, the Kz is calculated as 2 MD. Then, we calculate the value for the skin. As I mentioned earlier, the value of delta P at 1 hour can be obtained from the graph, which is 39. Put it back to the original equation of the skin, and we get St equal to 0.0812. Lastly, we compute the end period of the early radial flow region by using the two equations mentioned earlier, and we get 27 hours and 1.875 hours. Comparing the values, we expect the early radial flow region to end at approximately 1.875 hours. Now we proceed to early linear flow, and this is the region of the curve at which the early linear flow occurs. The first equation is a drawdown equation for the early linear flow. It is almost as similar as the previous drawdown equation, but this time we have to calculate the value for the convergent skin, SC. Convergent skin is an additional pressure drop that acts like a skin effect caused by the flow of fluid from formation until it converges down to the small well bore in the middle of the formation. It is defined in terms of the ratio of the permeability in the x direction over permeability in the z direction. It also involves the distance to the nearest vertical boundary, dz, and the net pay thickness, h. The second and third equation are the equation for the skin and the equation for the convergent skin. This diagram shows the difference of h, capital dz, and small dz. This slide shows the equations to calculate the start and the end of the early linear flow region. The difference between the two equations are, for the start of the early linear flow equation, it depends on the farthest distance to a vertical boundary, dz, and the vertical permeability, kz, while for the equation to calculate the end of the early linear flow, it depends on the effective completed length of the well, Lw, and the permeability in the direction parallel to the well, which is Ky. Let's see an example. A drawdown test has been conducted at well B, and these are the data obtained. First, we draw a graph of Pi minus Pwf versus time on a Cartesian plane. Then, we determine the slope, and we get 0.934 psia over the square root of hr. Then, we calculate the values for kx and kz. By using the equation of the gradient, we get kx equal to 404 md. And since the value of kx, kz is given as 8000, the kz is calculated as 19.8 md. Then, we calculate the values for SC and SD. The value of SC is 4.91 and the value for SD is 0. Lastly, we compute the expected time range for the early linear flow region. Since the producing well is assumed at the center of the formation, we divide the h by 2 to obtain the value of dz, and kz is equal to 20 md. Substitute the values back to the equation and we will get 0.675 hours. And then we assume that ky is equal to kx, which is 400 md. Substitute the values in the equation and we will get 7.5 hours. The first equation is a drawdown equation for the pseudo-radial flow. And pseudo-radial flow period will only occur if Lw over Bh is smaller than 0.45, at which the Bh is the dimension of the reservoir parallel to the wellbore. The terms of 162.6 Q d mu over the square root of Ky times Kx times h is the gradient of the curve. This diagram is to show the difference between Lw and Bh. Next, the equations to calculate the skin and the convergent skin are expressed at the top of this slide. The start of this flow period occurs when fluid flows from the well beyond the ends of the well bore, and the equations is expressed at the bottom of the slide. The end of the pseudo-radial flow period is the time at which the horizontal boundary effects first appear, or at which the radial flow pattern begins to be distorted. By comparing the values obtained from the two equations, the lowest value will be the end of this period. This diagram is to show the difference between dy and dx. Let's see an example. This is a drawdown test conducted at well C, and these are the data obtained. First, we plot the graph of Pi minus PWF versus time on a semi-log graph. Then, we determine the slope, and we get 15.3. Next, we compute the value for Kx and Ky. Since the value of Kx is given as 100, the Ky calculated is 50.2 MD. Then, we compute the values for Sc and Sd, and we get Sc equal to 5.13 and Sd equal to 0.057. Lastly, we compute the expected time range for the pseudo-radial flow region. We have concluded that the start of this period is 71.6 hours and the end of this period is 344 hours. That's the end of my presentation. Now, I would like to pass it to Yap to present about the advantages of the horizontal well testing.
Hi everyone, my name is Kian Yeap. I would like to present to you about the advantages of horizontal well testing. Before my presentation, please allow me to ask you one question. Why do we need horizontal well testing? We need horizontal well testing because there are many non-uniform skin effects along the well bore, and this will be very dangerous to the well. Besides, in horizontal well, the heterogeneity in vertical direction and lateral direction will greatly influence the productivity of the well. Now let's move on to the advantages of horizontal well testing. The advantages of horizontal well testing is all about the procedures is almost the same as the vertical well testing. Hence, the engineers will be very familiar with these procedures and they can easily apply their skills in horizontal well testing. Besides, the horizontal well testing can be applied to study the non-uniform skin effect along the well bore. The non-uniform distribution of the skin creates a challenging problem in the well. Hence, the well testing for vertical well cannot be directly applied in horizontal well. The interpretation of the skin effect and the well productivity also need to be modified. Besides, the horizontal well testing is very useful since it can study the heterogeneity of the vertical direction and lateral direction. This is because in horizontal well, both the vertical and lateral heterogeneity will influence the productivity very greatly. Besides, horizontal well can reduce the fluid velocity near the well bore and hence minimize the turbulence effect. In other words, a horizontal well enhance the perforated interval, reduce the wellbore turbulence, and increase the productivity. Horizontal well testing data is needed to achieve the maximum productivity. Besides, the horizontal well testing data is very important for the selective of completion along the horizontal well. After we getting the data, we can determine the error of the zonal isolation that can minimize the valve problems and damage. In short, the horizontal valve testing plays a very important role and have many advantages. With horizontal valve testing, we can identify the flow regimes, which give valuable information about the valve, such as the vertical and lateral heterogeneity of the valve bore storage effect, the skin effect, the boundary effect, the reservoir size, the productivity, and all this data is very important for an engineer to determine the completion of the well. Thank you.
Thanks Kian Yeap for telling us about the advantages of horizontal well testing. My name is Swee Tat. I will be continuing the presentation with limitation and improvement of horizontal well testing. Now, I would like to explain about the limitation of horizontal well testing. There are several limitations of horizontal well testing. First, by using horizontal well testing, it's impossible to get a wellbore pressure within the source because the wellbore pressure is calculated at a finite radius outside the source instead of inside the source. Secondly, it's difficult to conduct a realistic comparison between horizontal well and vertical productivities because both wellbore pressure are not computed at the same point. Thirdly, horizontal well testing need a longer test period to get the important parameters of the well. This is because the horizontal well test need to run longer tests with downhole, shut-in or drawdown interpretation with flow rate measurements. Hence, the well site real-time monitoring and interpretation are essential in order to have an optimum test length to achieve the test objective. Followed by evaluation of productivity in horizontal wells is subject to more uncertainties, and interpretation of well tests in horizontal well is much more difficult compared with counterparts in vertical wells. It is due to the wellbore storage effect, the 3D, three-dimensional nature of the flow geometry and lack of radial symmetry, and strong correlations between certain parameters make it more difficult to be interpreted. Lastly, zonal variation of vertical permeability and shear distribution will make the interpretation more complicated. During well-defined flow period, comparable to that of the infiniting radial flow period, which is free from storage and boundary effect of a vertical well, is not apparent for horizontal wells, largely because most horizontal wells exhibit partial penetration effect even when they are fully perforated. The next topic I will cover is what can we do to improve the horizontal well testing. First of all, longer the shut-in period in order to provide reliable late-time reservoir data. Secondly, implementation of downhole shut-in valves. This downhole shut-in valve is used to reduce the wellbore storage effect. Other than that, installation of permanent downhole gauge in specific wells per sector of the field, in association with specific sensor to monitor pressure at a single point or multi-points in the well in order to read the formation pressure directly. Furthermore, interference testing need to be done to establish the degree of communication between the wells, followed by identifying the early time pseudo-radial flow to obtain skin which caused by wellbore storage damage. Lastly, run tests in the pilot hole before kicking off to drill the horizontal borehole section. It is because these tests will possibly get usable estimates of horizontal and vertical permeability using modern wildlife test tools.